Okay, next up we have Alice Allen is going to be hosting some lightning talks for posters. And then after that, we're going to have the BOF on cost management on commercial cloud platforms.
Okay.
So, Alice, please take it away.
Yes, hold on. Okay, so the first speaker is David. So please raise your hand, David, and could somebody please promote him so he can, or unmute him so he can speak.
He should be able to unmute himself and speak now.
Yes, can you hear me?
Yes, go.
Testing, testing. You can hear me?
Yes.
All right, awesome. Yeah, there was a brief lag there. All right. So hello, everyone. My name is David Rodriguez. I am an astronomical data scientist at the Space Telescope Science Institute, and I work with MAST, the Mikulski Archive for Space Telescope. So my poster is about CAOM, the Common Archive Observation Model. It is something that we have implemented, and it's been developed for several years now between CADC, ESAC, and Space Telescope. So these are our Canadian and European archive counterparts. And the goal of CAOM is to consolidate metadata across missions, telescopes, archives into a standard model that can be queried very easily and shared across institutions. So in the brief amount of time, I just want to point out that MAST has millions of observations across over 20 different missions. So we're talking things like GALEX, TESS, Kepler, IUE, HST, JWST, PAN-STARRS, et cetera, all of them are processed through CAOM so that users can query it very easily without having to worry about the specifics of each mission. Furthermore, there's this little triangle that you can see on the plot between Space Telescope, CADC, and ESAC. When we reprocess or process for the first time HST data, we load it into CAOM via a serialization of the model as an XML file. This is harvested between all three institutes, and it is loaded independently for each one. This means that users can, for example, go to ESA Sky and get the same metadata that they would see in the MAST portal or on the equivalent CADC advanced search interfaces. So this really ties in to a lot of the interoperability discussions that we've been having, basically the ability to share metadata across archives. It's not quite yet a VO standard, but it has been presented in the past. And my hope is that over the next few years, it gets adopted more widely across other archives, and it becomes an IVOA standard that we can adopt more broadly. So with that, I think I am out of time.
Yep, thank you so much. Okay, next up is Carter. So,
all right. Hello, yes.
Okay, yes, I hear you. Go.
Okay, perfect. Hello, everybody. My name is Carter Ray. I am a first-year PhD student at Université de Montréal in Quebec. Today, I'm just going to briefly describe a project that I worked on when I was interning at the CFHT last year during my master's degree. What we did is we decided to approach or use a machine learning approach to IFU data. So if you're not familiar with IFUs, they give you spectacular amounts of information. Not only do they give you a basic 2D image, they also give you a spectra for each of those pixels. This is wonderful, but of course that creates a problem. When you use an IFU like the IFU that they have at CFHT called SATEL, which has over 4 million pixels, that means you have over 4 million spectra. So standard fitting techniques to pull out kinematic data from this or whatever you may want to take can take up to 3 weeks to run normally, even if it's highly parallelized, just due to the sheer amount of data that you have to go through. So our hope was to use machine learning to either speed up those algorithms or to completely replace those algorithms. And this, of course, take a look at the poster if you're interested, but the take home is that we were able to use a convolutional neural network to pull out some of the main features that the groups at CFHT are interested in studying. And we have a 2 order of magnitude speed up in time and computational efficiency compared to standard fitting methods. This is the first paper in a large series of papers that I'm leading as part of my PhD thesis, and they're all focused on machine learning and IFUs. That's it for me. Thank you.
Wow, thanks. You do have 20 more seconds.
Okay, sorry, I tried being as fast as possible. We're also, so this particular thing, if you're interested in Galaxy, or if you're interested in IFU data, not just at CFHT, this has actually been ported to Muse as well and other IFUs, and it actually works for any spectra, optical spectra. It doesn't necessarily have to be IFUs. And it's all available freely online at our GitHub page, Pamplemousse.
That was perfect. Thank you.
Thank you.
Next up is Patrick. So Patrick, please.
Yes, can you hear me?
Yep, go.
Perfect, thanks. Hello everyone, I'm Patrick and I'm a PhD student in astrophysics and the main developer of Colibri. You may remember on September, sorry, I hear an echo. I'll try it again. You may remember on September 22, 2017, IceCube has sent an alert about a high energy neutrino detection from outside our galaxy. But it took us a week to realize that the emission came from a nearby blazar from the TXS catalog. And this, although all information was known already at the time of the alert. So for example, the FITS files and the Fermilab catalogs were available, the Fermi Fava website was already running and showed a flaring state of the blazar, and so on. So basically everything was there, but the connection was missing. This is how Colibri started. We developed a user-friendly, highly interactive tool for tasks exactly like that. And in the section of the poster about use cases, you see 2 screenshots of our website. The left one is the default of our website and shows you the latest gamma ray bursts and neutrino events in a zoomable and pannable map so that you can get a visual impression of the latest events. In the central lists, all these transients are ordered by observation day. And we also show further information and visibility plots on the right side of the website. And yeah, for each transient that you can find there, you can perform a cone search showing known sources around the transient event. And this is shown in the right screenshot of that section. In the center of the screenshot, these known sources are ordered by separation to the central object, so to the transient object. And each source provides links to Simbad and current light curves from the Fermi and other websites. And I have to note that Colibri is still under development, and we plan to implement many new features like gravitational waves in the next weeks and months. And we are happy about your feature requests. If you have some, just write me. And in future, we will also have a mobile app for iOS and Android that alerts you in real time about gamma ray bursts and neutrino events. And we distribute it soon in our apps, in the App Store and Play Store. And at the end, I now just want to challenge you to go to our website, astro-colibri.com, and try to make the connection between the neutrino event from September 2017 and this famous TXS source, and tell me how long you took.
Thank you very much.
Thanks too.
Thank you. So
can you hear me?
Yes, thank you.
It's Fabian here. Okay. Hello, everyone. My name is Fabian Jankowski, and I'm a postdoc working on the MEATRAP project at the University of Manchester. MEATRAP is an instrument at the Meerkat telescope to search for fast radio bursts and radio pulsars. This is all done in real time and fully commensally. The Meerkat telescope is an array of 64 antennas and is the largest radio telescope in the Southern Hemisphere. Fast radio bursts are mysterious bursts of roughly millisecond duration that come from extragalactic distances. Most importantly, their nature is currently unknown. Now I want to talk a bit about this work. We are in the process of implementing a real-time triggering system for MEATRAP, which I present here. Our triggering system includes voltage ring buffers that retain about 50 seconds of data. This sets a hard real-time requirement on the software. On the poster, I show you a diagram of the real-time system in the middle. I will quickly run through that. The system first consists of the single pulse detection pipeline that identifies candidates. For that, we use Astro Accelerate. And most of the other software is there to ensure that the candidates are genuine astrophysical detections and to reduce the amount of false positive triggers. For example, we have implemented a multi-beam clustering and a known source matcher that flags known sources from various catalogs. Those two components already result in a reduction of about 70 to 90% in the number of candidates. A machine learning classifier will reduce that number further once it's fully deployed. From there onwards, we generate VO event packets and send them to a Telescope internal broker. The VO event then initiates a write-out of the voltage buffer data, which are transferred to an imaging node for further processing. I want to talk quickly about the proof of concept. We have tested, earlier this year, we tested the initial system on pulses from the Bright Vela pulsar. And on the right-hand side, you can see a snapshot image of the pulse and a higher resolution profile. So it works so far. And in the future, we will distribute our triggers to external facilities. So there will be many opportunities for collaboration. Thank you very much.
Thank you. And we have one more speaker.
Hi all, good evening, or depending on where you are. I want to present the Caracal, the containerized automated radio astronomy calibration pipeline. And if you're a radio astronomer, or if you know radio astronomer, what is meant by this is actually an end-to-end data reduction pipeline that transforms the signal from, or the recorded signal of a radio interferometer into an image or data cube. So the plan was to have it portable, tunable, and adjustable to science case and telescope, with an emphasis on MeerKAT. Now we are a team of 16 developers with a very mixed mix of astronomers, computer scientists, and some of them are students. So that requires a good time management. So what we are using is GitHub, as many people, and actually a good CI implementation, also Jenkins to do continuous testing of the data. At the core of the pipeline is Stimula, which is a mixture of containerization, using a few containerization techniques, and a programming user interface. We implement quality assessment and a remote inspection of the data. And this conference actually has many contributions of software development that actually go into our pipeline. So our pipeline is basically the proof of concept that these can all be combined in a very nice package. And we also have a few science papers already. The pipeline is public right now since May. And please contact me or have a look at the pipeline or the poster. Thank you.
Thank you, Yola. Okay, that's it for. Can we please thank our 5 fabulous speakers? Do we have a little applause for them? So you all did really well. Thanks so much.